Okay. Entanglement. The name itself suggests us that entanglement means getting entangled. Usually, quantum is resultant from the wave theory of quantum mechanics. Hence, whether entanglement exists or not is what we check. Of course, mathematical orientation is what I'm talking about. Usually, quantum entanglement arises. When does it arise? Arises or happens? It happens in multi-qubit system. In multi-qubit system. What is a multi-qubit system? If you ask me, of course, if you have checked the previous videos, you have this idea that usually the basic states are 0 and 1. I can get one more basic state using the superposition principle, that is alpha ket 0 plus beta ket 1. Okay. Apart from this, these are single qubit systems. These are single qubit systems. Then how do I get the concept of multi-qubit system? Multi-qubit system. It all starts with the tensor product. Okay. Suppose if I have something like ket xi1 is equal to alpha 1 ket 0 plus beta 1 ket 1 and ket xi2, this is equal to alpha 2 ket 0 plus beta 2 ket 1. If I have like this, and if I go with the tensor product of these two states or kets, tensor product is denoted by this symbol, then it gives rise to a multi-qubit system, which would be alpha 1 into alpha 2, ket 0, tensor product of ket 0 and ket 0, which I write in shorthand notation like this. Also different things like with ket 0 and alpha 1, I have alpha 1, beta 1, ket 0, ket 1. Okay, with beta 1, ket 1, I have beta 1, alpha 2, ket 1, 0 plus beta 1, beta 2, ket 1, 1 kind. Okay, now this is a 2-qubit system. How I have got this 2-qubit system? Using tensor product of quantum computing. Okay, now this entanglement happens in multi-qubit system. First thing that this I should be aware of. Again, what is a multi-qubit system? I am aware of. Now, this entanglement word, quantum entanglement or entanglement word was first coined by Einstein, Podolsky, and Rosell. Okay, in a research paper. In 1935, in a research paper. Okay. Hence, when I'm talking about quantum entanglement, I come across EPR states. These are also called Bell states, guys, about which I'll talk in a few minutes. Okay. Okay. Let's see first what exactly is quantum entanglement. Okay. What's the definition for entanglement or quantum entanglement? Well, let us see that. When we are, let us stick on to a 2-qubit system first, then extend it to an n-qubit system. Okay. How I will define it is when two systems are entangled, the state of the composite system, don't worry about this tough words. Composite system is nothing but this one. Together, the state of the composite system, if it can be described with reference to to the other state. Okay, other state. With respect to one state, if it is described with respect to other state, the state of one system can be described with respect to the other state. Then we say that both the states are entangled. Okay. Otherwise, if I cannot say anything about one state looking at the other one, then such states are such two states where we cannot draw conclusions. We cannot draw conclusions with respect to one another, I should say. Conclusions with respect to one another states, with respect to one another, then the states are not entangled. States are not entangled, or you can say they can be separable. They can be separable states. They can be called separable states. Also, there's another name, product state. They are also called product states. Okay. Of course, this is a physics or physical way of defining it. What if the system state of one system can be explained with respect to the with reference to the other system, then we say both the states are entangled. If no such conclusions can be drawn with respect to one another, then they are said to be separable states or product states. Okay, now this is all about the physics definition or physical definition of it. Now let me come to the mathematical definition of it. There is a small test to check whether the states are entangled or not. There is a test which I will give, which is very simple. Suppose if we consider states in CH, what's this notation for us? I'm in complex plane, guys. Complex. H stands for Hilbert space. Hilbert space. Of course, in the basic videos of complex, how the things are related to quantum I have discussed, you can just cross check. Consider the states in CH. Okay, in the set CH. What is CH? The complex Hilbert space. Okay, now I'll consider one state Ketzai, which is given by A, B, C, D. Okay, Ketzai is said to be separable. Is said to be separable if and only if AD is equal to BC. You remember this condition, right? And matrices and all that. In a similar way, if AD is equal to BC, then you can say they are separable. If they are not equal, then they are not separable. Okay. Now, let me show certain things about being separable and not being separable. Okay. There are three Bell states, guys. Again, about which I gave some explanation in one of my videos. Do check. There's a question that is, are Bell states or these are also called EPR states, are Bell states entangled? Okay, are Bell states entangled is the question. What are Bell states? Let me write here. Okay, beta 0, 0 is nothing but 1 by root 2 1 0 0 1. Of course, this has another notation also. 1 by root 2 0 0 plus 1 1. I can just show you how things are happening here in case you have a doubt. This is nothing but the tensor product of 0 0. Ket 0 with ket 0. Okay, just see what ket 0 is 1 0 and tensor product of ket 0 is 1 0. And all of you know, you can check again my previous videos with the tensor product. All of you know what's tensor product, right? 1 1 0 0, 1, 0. Okay. So what do I get? Okay, this first part is this. This first part I'm calculating. What do I get? 1, 0, 0, 0. You can check that. Coming to the second part. See, this is tensor shorthand notation for tensor product. What is shorthand notation? Writing ket 1 1 is nothing but shorthand notation for tensor product. What is ket 1? It is 0 1. Tensor product with 0 1. Okay, so what do I get finally? 0 with 0 1, 1 with 0 1. So what I will be getting would be 0 0 and 0 1. Okay, of course, this is 1 by root 2. So this value is 1 by root 2, 1 0 0 1. That's how I got Bell state, first Bell state, guys, beta 0 0. Okay, just the tensor product. Don't get scared looking at it. Okay, I need to check whether the Bell states are all entangled or not. I have just given the first Bell state. How do I check it? There's a small test for a 2-qubit system. What is that? AD is equal to BC or not is what I will check. Okay. So A, B, C, D. Okay. AD is what? 1 by root 2. Okay. BC is what? 0. Both are not equal. Hence, what can I say? Hence, beta 0 0. How you conclude is also important. The first EPR state is entangled. See, if both would have been equal, then they are not entangled or separable. Okay. Now coming to the next EPR state, beta 0 1, guys. 1 by root 2, 0 1 1 0. Okay, you can kindly check the tensor product notation of it, but here I am going to check the entanglement. So I just strictly stick on to it. Okay, AD is what? 0. BC is what? 1. Both are not equal. Hence again, this is also not entangled. Beta 1 0. This is equal to 1 by root 2. 1 0 0 minus 1. Okay, again AD is what? Minus 1. BC is what? 0. Again, both are not equal. Okay, finally, the last one, beta 1 1 is nothing but 1 by root 2, 0, 1, minus 1, 0. Okay, so what is this? AD minus BC, AD is equal to BC or not? AD is 0, BC is minus 1. Both are again not equal. Hence, all the Bell states are entangled. Okay, since AD is not equal to BC, all are entangled. All are entangled. That is, they are not separable. They are not separable. Entangled means what? Looking at one, with respect to one, you can tell about the properties of the other one. Okay. There are some more other things which you can check. There are some more other examples which you can check whether they are entangled or not. Suppose if I consider an example, one more example I will consider. Apart from the EPR states, it's a standard question. So do remember that. Consider a 2-qubit system. Consider a 2-qubit system. 2-qubit system. Ket 0 0. Okay. Operate on the state H tensor product of H. Okay. And check whether the resultant is entangled. Whether the resultant is entangled. Okay. So what do I do? H cross H. This is equal to 1 by 2. Of course, you need to know what H gate is, guys. I'll just write here I made a mention of it in my other videos. 1, 1, 1 minus 1. Okay. Now when I go with tensor product, 1, 1, 1 minus 1. If I say h, then what happens? 1 by 2, h, h, h minus h. So how does this look like? 1 by 2, 1, 1, 1 minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1. Okay. The 2 by 2 1 got transformed to 4 by 4. Now this has to be operated on get 0, 0. Okay. H, tensor product of H has to be operated on 0, 0. Okay. So I know what is 0, 0, right? It is 1 by 2, 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1, 1, 1, 1 minus 1, 1 minus 1. Okay. And this one is 1, 0, 0, 0. Okay. So just multiply, do matrix multiplication, see what happens. 1 by 2. 1, first element is 1, next element is also 1, next element is 1, next element is 1. Now see here what happens. What is AD? AD is 1. What is BC? It is also 1. Hence, what can I say about it? The resultant state is, of course, 1 by 2 it is, guys. I'm sorry. 1 by 2 is also multiplied, right? Resultant state is not entangled, or you can say it is separable, or it is product space. I can separately write, I can separate and write, because of which it is called product state, not space, state. Product, it is also called product state. This is all about quantum entanglement, guys. There are different examples. You can check them out. I can as well share some more problems. Okay. As of now, I will end this video. I hope this has given some clarity about quantum entanglement. Okay.